I should do the tradition. Hi, I'm David. I'm the coordinator of the Maths Learning Centre. It's semester 1, 2018, and this is a revision seminar for Algebra II. All right. I've been enjoying the fractal this week. It's been fun. Okay. So I've got all these different requests. I don't really know what order to do them in because I don't really know where they come in the course. But I will take them in the order they arrived, and it will require me to find places in the lectures that talk about them. So I'm just going to see if I can find them. I was sent just a couple of specific pages. How do you know which lecture is which? Okay. Cool. I mean, that's exactly what would happen if I wrote lecture notes too, but I think when I wrote them I just had a rolling page number. And any time I forgot, I just made sure I picked a number that was greater than the numbers I'd already done and told you what was the page before it. Okay, so I've been asked to talk about ordered bases. So just a second, from the shape of the things we've listed here, I have a feeling that almost all of these are to do with vector spaces and not groups.
In the exam, in the mid-semester test, we did all of the group content, and in the exam, he's not covering anything we did in the mid-semester test.
Oh, right.
Yeah, so
it's only the second 2 days of the course that
it's like groups acting on sets, and then vector spaces. It's pretty much what we've got.
Cool. Radio. Okay. Sorry? I suppose. Okay, so that makes sense, and it's good that I already had a group thing that I did with people in 2015 on the website. I don't know if you knew it was there, but it is. Okay, and that does explain why I did that in the mid-semester break in that year, because there was a test about it, so it explains some things. Okay, so ordered bases. So my particular idea off the top of my head is that I think it is what I think it is. Okay, and I think the point is to turn vector space things, which currently are not really about matrices and are just general stuff, into matrix stuff. That's the goal here, I think. Turn vector space things into matrix things. Okay. That's what I'm going to try and talk about, if I understand what's going on here well. Yep. All right. So the idea is that any vector space, is that only the finite dimensional ones? Maybe. Vector spaces have a basis. And so you might have V something like that. There may be a little star there. It's like, you know, batteries not included. Which says that there might be some that don't if they're crazy enough. So, sorry, I should be a little less frivolous. So, I think that there are some vector spaces that don't have a basis unless if you're not allowed to use the axiom of choice. Yeah. So, anyway, most vector spaces have basis, and that's like that. And any vector in the vector space can be written as a linear combination of that basis. Of basis in exactly one way. Like that. I'm pretty sure your lecturer doesn't put underlines on their V's, but I can't stop doing that because I teach mostly first year. So, okay. And so what I can do is I can create a set of coordinates for the vector v using those coefficients. Traditionally, you put them as a column vector, I believe, actually. So I'm just going to check something in the way the notation was used. Yep, here it is here. Okay. Like that. Sweet. So, from the pure maths perspective, vectors don't already have coordinates of their own. Okay, vectors are just things that add and do scalar multiplication. And I have to create coordinates by doing by finding a basis and finding what the coefficients are that goes with the basis. And so I can create this set of coordinates for V. But the thing is, if I choose a different basis, I'll get a different set of coordinates. Now, over in physics, they don't bat an eyelid at this. It's like, well, I can just put my coordinate axes in space wherever I want, and I can use coordinates according to whatever axes I think. And that's essentially what we're doing here. We're drawing coordinate axes. So the idea here, for example, here in R2, which is a plane that has the origin in it. Traditionally, we already have coordinate axes. So I could choose a vector here and a vector here to be my basis. And what that would do is that would cause me to create a set of coordinate axes which we marked out in vectors of those lengths. And I could locate any point in R2 as like, you know, this one would have coordinates 1, 2, because it's at the position 1, 2. That's how I do coordinates in R2 normally that way. But it's also 1 of this vector and 2 of this vector. So V is 1 of this vector and 2 of this vector. Damn it. V is 1 of this vector and 2 of this vector. That's how I get to that point. using my vector coordinates. But I could just as easily have chosen a completely different basis. You know, maybe I'd choose something like that. And then the same point, which was here, is now made in a completely different way. It looks like it's, let's change my colour. It looks like it's V is now, it's like about 1.5 of that vector and -1 of the other vector. And so I could use the coordinates here are 1, 2, but the coordinates here are 3 on 2 minus 1. And so that's what I'm doing. I can have any point which exists in the vector space independently, and I can use any basis and find coordinates for that point according to whatever basis I like. Cool. Okay. That's the basic idea of these things. But the point is that to do them as coordinates, I have to keep track of which vector is first in my list. Okay, so the idea is that this one goes with a specific vector, and this is the second vector. I could have chosen the other one to be my first vector, and this one to be my first vector, and this one to be my second vector, in which case the coordinates would have been -1, 3 on 2. So this could have been vector 1, and this could have been vector 2, like that. But I could just as easily have tried it the other way around. And done this one as vector 1 and this one as vector 2, in which case my V would have come out to have a different set of coordinates. Because the specific position in the coordinates refers to the specific vector. So if I put my vectors in a different order, my coordinates will have to go in a different order as well, because they belong to certain vectors. And that's what your lecturer is talking about with an ordered basis. Okay, normally when you talk about a basis, it's just a set, doesn't really matter what order it's in, because you can figure out, you know which vector is which anyway, and so because when you write it as a linear combination, the vector that you're with is there in the representation. You don't have to worry about what order they're in. But if you're just writing a list of coordinates, then the first one has to always refer to the same vector. There's nothing stopping me writing this the other way around, but now the first one refers to a different vector than it did before. And so that's the idea of an ordered basis. Ordered basis allows you to have, you know, the coordinates refer to vector in order in the list. Okay. Cool. So that's what an ordered basis is, and so it's not particularly relevant until you start trying to do things with matrices. So because we can now represent our vectors as sets of coordinates, now when we were in Maths 1, first year Maths, that's what we started with. All vectors were sets of coordinates to begin with. Now we've discovered that there are all these vector spaces that don't have coordinates to start with, and we have to create coordinates for them. But now we've created coordinates for our vector space, we can now start doing things with matrices, because matrices can act on sets of vectors. Okay. I need an example, and this is a bit thin on examples. My favourite examples are polynomials, because they don't look like vectors to begin with. So, but I will do 2 different ones. So let me just try some things out and see if I can get somewhere useful with this. And we may end up talking about the things that come later with this. But I'm just going to do R2 as normal. And I'm going to think about we're going to have two bases. We've got our standard basis, basis 1, which I will call B1, is my standard basis. It's 1, 0 and 0, 1. And basis 2, I'm going to use, see if I can use ones that are rather similar to this. 1 minus a half and 2, 1. You right? Yeah. You're not all right?
It's just struggling writing down vectors.
Okay. So any vector in R2 can be written in terms of both of those bases. So, for example, the vector, 5, 7 is, in terms of the first basis, it's just 5, 7. And I'm going to put a little 1 here to say it's in terms of the first basis. This is in terms of basis number 1. Because, that's already the basis that creates the coordinates that this vector has. But it would be something else in terms of basis 2. And I do not like my chances of coming up with that on my own. I would have to figure that out. And if I was doing that in Maths 1B, I would use matrices to do that, right? So I would actually just try and solve this. So 5, 7 is something times 1 minus a half plus something times 2, 1. And so AB 1 minus a half, 2, 1, 5, 7, and I would figure out what I needed to do that. I mean, that's what I would do. So, this plus half of that would be 0, this plus half of that would be 2, this plus half of that would be 9.5, which would be 19 over 2. And then I would have to I could do the subtraction now. That'll be fun. Do you know what? I'm not going to write it as 19 over 2. I'm going to write it as 9.5 because that makes sense to me. So I take this off of that. 5 minus 9.5 would be negative 4 minus a half, which would be negative 4.5. Okay, and then I'll divide by 2. So that'll be 4.5 and a quarter, which would be 4 3/4. Okay. So minus 9 over 2 and 16. All right, cool. And so it turns out that this is actually minus 9 over 2 and 19 over 4 to get those coordinates, which I could have chosen something easier, but that's all right. Okay, lovely. So the thing is, this process here would allow me to convert from the old coordinates to the new coordinates, and I could actually copy this process, and in fact what I've done is I've multiplied by the inverse of this matrix in order to get down to here. And so that's the change of basis that I can do if I want to. So in fact I should be able to go to convert from coordinates in B1 to coordinates in B2, multiply by 1, 2 minus a half, 1 inverse, which is cool. Yay. All right, that's nice. So the thing is that I could now do anything that I could do in this basis with linear transformations and stuff, I could do in this basis as well. So I could just as easily go, so, consider L, which sends R2 to R2 by x minus y, 2x, something like that. So I can create a matrix for this depending on the coordinates that I use for that. And at the moment it's defined in terms of the coordinates of the original basis, but I can redefine it in terms of the new basis. So this is what it does. So technically, this is L of xy according to basis 1 is x minus y 2x according to basis 1. I mean, that's technically what we've got. And so it should be possible to figure out what it does in the other basis as well. Okay? I don't know this off the top of my head. I'm just going to try and make it up. I've got two ways of trying to achieve this. One is, so what I want to know is, what is L of AB in terms of the new basis? So I'm not going to use xy because I don't want to get myself confused. This is what I want to know. So I could convert from B2 back to A, back to B1, then do the linear transformation, and then convert from B1 to B2, and that would do the trick. So let's just see. L of AB in terms of B2 is L of A lots of 1 minus a half plus B lots of 2, 1. I mean, that's what it really is, because the A and the B are the coefficients of the basis. There's our possum. And so this should be A of L of 1 minus a half plus B of L of 2, 1. Which we know what they are. They are x minus y, which is 1 minus a half, and 2x, which is 2, and 2, 1 would be 2 minus 1, which is 1, and 2x, which is 4. And these are all in terms of basis 1, just to make sure we're all good with this. But I really wanted in terms of basis 2, and so I had to convert them to basis 2. And so I'm going to have to figure out what 1, 4 and 3 on 2, 2 are in terms of basis 2. Damn it. So 3 on 2, 2 in basis 1. I'm going to need to figure out what that is in basis 2. And just a second, I figured out that convert from basis 1 to basis 2, I need to multiply by the inverse of 1, 2 minus a half 1, which I didn't figure out what it was. Curses. But I can track through the same thing that I did before. What did I do? I did row 2 plus a half of row 1. And then I did row 1 minus row 2, and I did row 2 divided by 2. Okay, so I need to do those things. So this plus a half of that, just a second. So we started with 3 on 2, 2. We're going to do row 2 plus a half of row 1, which would be 2 plus 3/4, which is whatever 2 3/4 is. And then we're going to do row 1 minus row 2, which would be 3 on 2 minus 2 minus 3/4. 3 on 2 minus 3/4 would be 3/4. And 3/4 minus 2 would be 1 1/4. And then I'm going to divide by 2 in that second position. Okay. So in this position here, I was copying my row operations. From before, so that I didn't have to actually figure out my matrix. So 1 1/4 is 5/4, 1 3/8 is 11/8. And 1 4 row 2 plus half of row 1, 4 1/2. row 1 minus row 2. 1 minus 4 will be negative 3 minus a half. I hope you don't mind my idiosyncratic way of doing fractions. 2 1/4. So we've got that 1, 4 in basis 1 is actually minus 3 1/2, which is 7 over 2, and 2 1/4, which would be 9 quarters in basis 1. So, where were we? L of AB in basis 2 is A of 5 quarters 11/8 in basis 2 plus B of 7 over 2, 9 quarters in basis 2. And that's whatever it is. You know what? We could do it as a matrix. That's more fun. Here we go. Yay! Okay. That's nice. So that's great. That's not the best way, but I just wanted to think it through to make sure that I knew what was happening. The thing is that this first column here, what the hell? This first column here is what I did by converting this 1, 4 into basis 2, and I know I can convert into basis 2 by multiplying by the inverse of this matrix. And so what I could have done is I could have noticed that L of AB in B2 is L of 1 minus a half to 1 times AB in basis 1 now, because that's how to get it back to basis 1. And then I could do the matrix that goes with L. So at this stage, just note L of xy was x minus y 2x. Oh crap, sorry. X minus y plus 2x, which is 1 minus 1 lots of xy and 2, 0 lots of xy. And so therefore, where were we? So just making sure we know what's going on here. This is now in B1. And then in B1, this is how to do L. And this is all in B1. But now I have to convert back to B2, and the way to convert back to B2 is to do the inverse of this matrix. So this is all in terms of B2 now. Sweet. So now we've figured out that if I'm doing everything in terms of B2, so in basis B2, L of AB is 1 minus a half to 1 inverse, 1, 2 minus 1, 0, 1, 2 minus a half, 1 times AB. Which would be a different matrix than it was before. And in fact, that should come out to this matrix here, hopefully. Possum agrees. So is that a sort of thing that happened in this course, where you would have to do that sort of thing? No?
Yeah, not like that.
No?
Not specifically. But yeah, the change of basis.
The change of basis thing with the inverses and stuff. Yeah. So it looks like just as a summary from this one example, and I'm going to abstract, so hopefully it works. If you have one basis already written in terms of another, so if you have basis, so let's sum this up. Yeah, we have basis B1 and another basis B2, and we already have vectors that are in terms of B1, and as long as we know how to write B2 in terms of B1, we can convert from 2 to 1 and vice versa. So let's call this one U1 up to UN, and this one V1 up to Vn. Can I call them BU and BV? Because then that makes me feel better. And so I can go like this. I'm saying if V1 is like A1, 1, U1 up to A, 1N, UN up to Vn, like that, then it must be true that a coordinate in terms of the B basis, is there a symbol for the coordinates in terms of a basis? So if I have just a random vector in terms of basis number V, basis V, then that should be okay, so if it was like some multiple of V1, then it would be that multiple of all of these.
So it's
Yeah.
supposed to be a U on the second to bottom line at the end.
Yes, it is. So what I did with my other example is I had my second basis, and I already had those written in terms of the first basis, and when I put them as columns, it became the matrix that converted from my new basis to my old basis. And so this should be the matrix that has U1 which has unhelpfully got its indices in the opposite order than you would normally expect. Like that. So this one is just the coordinates of V1 in BU up to the coordinates of Vn in BU. Sweet. And I shall call that matrix A. So what that means, if I want to convert back again, I can do the inverse. Like that. And now if I wanted to do a linear transformation, so if linear transformation goes from wherever it goes to wherever it goes, vector space into some other vector space. Then I should be able to write that in terms of a matrix. No, I choose not to do that. I'm going to do a linear transformation from the vector space to itself. If L sends vector space to itself, then I should be able to do a square matrix. I should be able to rewrite that as a matrix too. So L into a vector in terms of B1, L of W will be some matrix. Too many letters, people. I'm going to call it C because I don't want to use B anymore. Some matrix times W in terms of B1. And that C will be made of columns which are the coordinates of the basis in terms of B1. And so this one will be made of all these columns, and this will be L of U1 in terms of B1, and this one will be up to L of UN in terms of B1. Same as what happened when we did it in Maths 1B. The matrix for a linear transformation in terms of a certain basis just has the coordinates for the basis vectors in the order it's in. Right, which is what happened in our example. And then if you want to do the linear transformation in terms of the other basis, then we can go that L of W is a W in terms of basis B2. Right. And that happened to us. So let's just go back and compare that to what actually happened here. See, this is one of the problems with abstract algebra. You might know what you're doing, but writing it down in general terms is really hard. And conversely, if it's written down in general terms, as it is in the lecture notes, figuring out whether the thing that you're doing is the thing that's described is really hard. So I'm just going to go back and compare what happened here. So this one is what the linear transformation did to 1, 0, apparently. Yes, it did, because it had x plus y, and then 2x, and this is what it, x minus, okay, cool. So let's just go back to where we were from the example. L of AB in terms of, in basis 2, L of AB was 1, 2, minus a half 1 inverse, 1, 2, minus 1, 0, 1, 2, minus 1, a half 1 times AB. And this one, well, L of 1, 0 is 1 minus 0, 2 times 1, which is 1, 2. And L of 0, 1 was 0 minus 1, 2 times 0, which is negative 1, 0. And so that's good. The linear transformation matrix had the columns as the coordinates of L of the basis in the coordinates. That's good. And this one is the actual basis, right? That was the basis. So it totally works. Good-o. All right. Does that? Well, I don't know. It helps me. I hope you feel better. I feel better. The thing is that it would be really cool to do this in terms of something that didn't already have coordinates. Because one of the problems with this is that it already has coordinates, which can make it a bit confusing switching basis when you've already got a basis that's already written in terms of coordinates. And so I have a feeling that that thing that you sent had an exam question from 2016. Ah, yeah, okay, that's fine. Okay. So, that I can do. So, therefore, anything that I used to know about matrices from before can now apply to this. And that's why I might be interested in doing something like diagonalizing a matrix. because I can just apply that to matrices like I used to. Oh, wow. So there's an example in the notes here of having your original vector space as the 2 by 2 matrices going into R3 like this. And the thing is that x, y, z, t here, I could make a basis for this out of those 4 matrices. And so therefore I can create coordinates in terms of that basis, and this matrix is now a 4-dimensional vector, which is x, y, z, t. And so I can now create this, if I have a linear transformation that does this, I can now think of it as just a vector linear transformation and write the matrix in the appropriate way. This one's actually a little easier than what we had before, because what I was doing then was changing. This one is writing both of them in terms of a basis, and then that allows me to just write it as a matrix the way I used to. So this example here, look, I'm just going to stick, if you don't mind. So it's x minus y, 2x, 3x plus 1y plus 5t. And so I'm now thinking of my matrix not as a matrix, but as a vector which lists what's in the matrix. But now if I do if I change the basis, then the linear transformation would have a different formula. So if I, instead of using this as my basis for the 2 by 2 matrices, I used, 1, 1, and 1, 1, 1, and 1, 1, 1, and something else, and 1, 1, 1, 1, then I would get different basis for this, and so I would have a different formula. Okay. Cool. Well, since we're talking matrices, let's have a chat. Can someone tell me what an adjoint is? Is that a matrix thing, or is that something else?
It's something else.
It's a vector space made of linear transformations? No?
It's kind of. If you have a linear transformation from B to W, it's the one that goes from W to A.
Okay. So it's sort of like an inverse.
Yes.
Okay. All right, I might talk about that separately. But while we're talking matrices, let's have a look at these orthogonal diagonalizations and or Jordan canonical forms, eh? Are they late in the piece or early? I would imagine them to be after we introduce matrices, which is what we just did here. After bilinear forms. Oh, okay. So does that mean that I really should talk about adjoints? Do they come into it at all? Probably not. All right, so here we are making matrices, yeah? Okay. Orthogonal diagonalization of self-adjoint endomorphisms of a finite inner product space. Quick eagle piggle, catch maker packer's ogpog before it hits the ninky knock. I'm just reading. So, as far as I can tell, we did some, vague general things on linear transformations and stuff, and then we went, right, let's now think completely separately and turn everything off, and now we're talking about matrices over fields. Okay. Okay. So I presume that we can have a notation which is n, and they're square matrices. So Mn of F is n by n matrices with entries from F, apparently. Okay, and to orthogonally diagonalize them, I imagine we have to find eigenvalues like we used to back in first year. All right. I have really no idea what's going on, but I'm just going to go from here. But we can make eigenvectors, certainly. So if A is one of these matrices, then eigenvector V is a non-zero vector. Yeah. With AV is lambda V for some lambda in F, and eigenvalue V lambda is a number with a V not equal to 0 so that AV is lambda V. Okay, cool. So given, okay, so my understanding is that it should technically be possible to do all the things that we used to do with matrices, but with our field now. It's just that my field might be 0 more often than my old field was. So R is only 0 once, but you know, for example, the standard, the finite field of order 3 is 0 once every 3 times when you add them together, and so expanding brackets can cause some interesting things to happen. Oh, that's cool. So it says here that without loss of generality, there is a monic polynomial of degree less than or equal to n squared, such that Q of the original matrix is 0. Well, that's the Cayley-Hamilton theorem. Honestly, people. Not that we have determinants, though. So, oh, we do. So just summing this all up, there are determinants okay. Just a second. Do we still make characteristic polynomials in this course? Oh, there it is.
Yeah, and it popped up halfway through.
And it's still the same thing that it used to be. Okay. Sure. So we still have all the things we used to have. Characteristic polynomial A is the determinant of x minus A. Okay? And it will tell you what the eigenvalues are. Because the way that it used to do still applies to fields, because the only thing that my proof hinged upon was that multiplying stuff together and getting the answer 0 meant that one of those things had to be 0. And that's still true in a field. And so I don't need, because it's a field, I can use all of the same arguments I used for the other thing. So Characteristic polynomial for that is that. And then if you factorize, interestingly, it might not factorize inside your field. So if your field is algebraically closed, then that'll be good, like the complex numbers. But if it's not, there might actually be some less eigenvalues than you thought there were. So px equals, stuff like that. And then the solutions to those little polynomials equal to 0 will be the eigenvalues. And so we'll get, px equals 0 implies that x is an eigenvalue. All right. So therefore, we're going to get up to n eigenvalues, but it's not like we used to have where there had to be exactly n, because we may not have a bigger field in which to find them. Though technically, any polynomial can help you create a bigger field where it has solutions. Did you do extension fields? Okay, it's in a different course. Technically, in the same way that we found solutions to x squared equals -1 in the real numbers and produced the complex numbers above them, we can do that with any field if we want, but that's a bit philosophically interesting. So at this point, we'll have up to n eigenvalues, but it depends on whether these things have solutions or not inside your field.
We always said algebraically closed field when we were doing this stuff. So
Oh,
we
okay.
always just had F.
Okay.
I think.
If F is algebraically closed. All right, cool. Which is how we got around it in Maths 1 when we were using the real numbers, and then we said, oh, there's exactly n eigenvalues, except that we might have to use the complex numbers to do that. And so what we went up to an algebraically closed field so that we could do it. Technically, if you're using a finite field, there are no finite algebraically closed fields. And so you would have to extend it upwards forever to do that. Anyway, all fun and games. Okay, so in essence, it's really just the real numbers, like the complex numbers. That's really what we're thinking in here. Okay. Okay, and so you would still, because we can do matrix stuff, you can still find the eigenvalues. So the question is whether there are vectors to go with those eigenvalues. Because even if it was an algebraically closed field like the complex numbers, there were times when your eigenvectors values didn't have, like if your eigenvalue appeared like 6 times in the list, it might not have 6 dimensions worth of eigenvalues, vectors. It might only have 5. And so the question is whether you can do that. And so it used to be true that if you created a matrix out of eigenvectors, you could diagonalize a matrix. So we used to be able to go, so if we're lucky, we can take our original matrix and we can multiply it by a matrix here and a matrix here, and it will come out to be a diagonal matrix if we're lucky. And the only way to make that happen is for this matrix to be made of eigenvectors. And this would be diagonal entries the diagonal entries of the matching eigenvalues. And that's great. But the problem with it is that if you don't have enough eigenvectors that are linearly independent to produce a matrix P that's invertible, you won't be able to do this. It won't work if the eigenvectors aren't linearly independent, because the only way to make an invertible matrix out of vectors is if the vectors are linearly independent. And so what we have to do is that we have to create something that's not necessarily going to come out to a diagonal matrix. It might just come out to something else, and use some other vectors in these positions instead. And that's what the Jordan canonical form is for, as far as I'm aware. As long as I can actually find it in the notes. Just looking to see if I can find stuff. So if this is an eigenvalue, then Q0 is a minimum polynomial. Oh, okay. So the characteristic polynomial has to divide into the minimum polynomial. That's cool. Huh. But the characteristic polynomial might not be the minimum polynomial.
Yeah, it would be bigger.
Usually bigger than smaller.
Just a second. If something's an eigenvalue, then it is a zero of the minimum polynomial as well, which means that the minimum polynomial might be bigger than the characteristic polynomial?
Like
Higher degree.
Yeah, higher degree. Oh, I know, the characteristic can be that degree.
Oh, okay.
Yeah.
Oh, okay, because the characteristic one might have the eigenvalue there more times.
Yeah.
Yeah.
Okay. Okay.
They look the same, just one has some extra powers.
Right. And the minimum polynomial is the smallest polynomial of matrices that produces the zero vector. Okay. All right. Good, good, good. So just to make sure I've got this down pat, the minimum polynomial is the smallest degree monic polynomial with Q of the matrix being the zero matrix. Okay. And the characteristic polynomial is the determinant of, and it's traditionally called P, according to this, P of x, which is the one which is the determinant of xi minus a, which is necessarily monic as well. And that's why you do the xi minus a, not the a minus xi, because you're guaranteed, if you do the a minus xi, then the first term might be minus x to the n. So this is monic 2. And what we're saying is that any zero of the minimum polynomial, any zero of the characteristic polynomial is a zero of the minimum polynomial as well. Yeah. So if we've got that, so lambda is an eigenvalue of A, which means that P of lambda is 0, and that implies that Q of lambda is 0 as well. Okay. So any zero of the characteristic polynomial is a zero of the minimum polynomial. And so that, and if it is a zero of the minimum polynomial, then that's cool. So this is saying that if it is a root of the minimum polynomial, then you have to be able to factorize it, because that's how polynomials behave. And then this is monic of this is monic. And so if I sub the matrix into it, it can't come out to 0 because Q0 was the minimum one. And so therefore, if there must be a vector I can multiply this matrix by so that it isn't the 0 vector, because this matrix isn't the 0 matrix. Yeah? Because, yeah, if something isn't the 0, if something is the 0 matrix, then no matter what you multiply it by, you'll always get the 0 vector afterwards. And if it's not the 0 matrix, then you should be able to find something to multiply it by so you don't get 0 afterwards. Okay, and so let's define W to be this. Then A minus lambda, is that a 1?
He's right, 1 is the identity matrix instead of I. It's the identity matrix.
A minus lambda I times W is A minus lambda I times Q1 of A times V, which is Q0 of A times V. Yep. Which is 0 because why? A minus lambda I times W.
Is it like...
Oh, and the minimum polynomial of A is the 0 matrix, right?
Yeah, and is it like
Okay.
He's putting the log root back in, right?
Yeah. So his A minus lambda I is what you would do to, like this is the minimum polynomial because it was factorized. And we subbed A into this polynomial, which is the same as subbing A into this polynomial, which is the same as subbing A into this polynomial. And when you sub A into that polynomial, it comes out as the 0 matrix. Right. Sweet. And so this comes out as 0. And so AW is lambda W, and therefore W is an eigenvector of A. Right. Where W was QA. Right. And it has eigenvalue lambda. Ah. Okay. So that tells us how to find a new vector that was still an eigenvector, but wasn't made out of the things that we had already. Oh, okay, right. So claim so I'm presuming that these vectors here, that's an eigenvector and these are the other ones I made from it? What the hell does this mean? Is it several pages ago that we referred to these objects?
These things, yeah. This one too.
Wow. I'm certainly enjoying this. Okay, which may or may not be sarcastic. So I presume it's like the other things, like it's the other not quite eigenvectors. Well, I have a feeling that they are the not quite eigenvectors.
Okay, so I've got, so with the super basis, is that over the next page? So he constructs a basis out of this ridiculous thing. The V's are the eigenvectors, the W's are an ordered basis, the K's are something else. K's? Such that? Oh, yeah, the K's, okay, the K's with the W
But doesn't that make the k's eigenvectors anyway? Doesn't that make the k's eigenvectors?
They're a complementary subspace.
Just that the kernel of A is the vectors that you can multiply A by to get 0, which means they're eigenvectors, right? So are these the eigenvectors that go with non-zero eigenvalues then?
That would seem like a, yeah, that seems like
Seems like
but ultimately what this is doing towards.
And this is just everything else we need. So these are the non-zero, these are the eigenvectors that go with non-zero eigenvalues. These are a basis for the kernel. And this is enough extra stuff to...
No, all of the W's in the case. W and K are the two complementary subspaces of the kernel of A. And he combines...
Is one of them the kernel?
Together.
No, together they are a basis for the kernel. They're like the basis for the complementary subspaces. And then what he builds towards here is that he arranges them in such a way that he gets a nice ordered basis for the linear transformation.
Which creates this magical matrix.
Which leads to,
a lot of
yeah.
magic.
Right.
Yeah.
Oh, come on. And I wasn't even there. I set myself these difficult tasks. So, apparently, because of all of this stuff, I can then create this Jordan canonical form.
The important thing is knowing that you can create the Jordan canonical form. There is no way any of this getting there gets examined.
But we create the Jordan canonical form from the minimum polynomial, not the characteristic polynomial. Sorry?
I mean, the important thing with those was just to get the eigenvectors. So, like, you could use either, really. You just had a convenient way of using both to show that something was. And that feels like a bit of an aside, if anything.
So just making sure I understand how this works. This is a minimum polynomial. This is its characteristic polynomial, which has higher powers of these things than those things. And so the fact that the minimum polynomial has fewer of these x minus 2's than this one does means that I would love there to be 3 dimensions worth of eigenspace to go with this eigenvalue of 2, but I only have 1. Yeah. Okay. And right, I'm just going to write this on my piece of paper here. So if I've got this right, if you find an the characteristic polynomial and the powers in it don't and you know the powers in the characteristic polynomial, we have to add up to how many columns there are in your matrix. But then you find the eigenvectors of those and they don't add up to and the dimensions don't add up, then that tells you what the minimum polynomial is.
We didn't do that explicitly, but that seems likely.
That seems likely. Okay. All right. So it seems to me that if I was able to do this, so I'm just making sure this works. So if your minimum polynomial, so this is his example, but I'm just going to do one of my own. I'm going to use his example, and then I might try and do one of my own. So this is the smallest polynomial that my function, that my matrix satisfies, and then the characteristic polynomial was that. And so what here we have is that these match. They match. And we've got a difference of 2. And this one's got a difference of 2. And these ones match. the frell is going on here? Such a good idea. Okay, so it's not just the differences, it's also how many there are.
Yeah, it's not quite that clear cut. The relationship wasn't really clearly explained in lectures, I didn't think. In the tutorial, it got a bit clearer. There were really good practical examples in the last tutorial.
Do you want me to email you the two questions?
Sure.
I think the tutorial room is a lot clearer. And it gave you like a concrete example of
I just sent
here's a
it.
variable, here's a characteristic, build a matrix. And I think that's likely all we'll get in the exam. Like Nick even said, this came so late, there's only so much you can ask about it. So
Just press it, it's not an exist.
When I put this on the website, it's just going to say Revision Seminar 2018. You can find in it what you will.
Did the emails come through?
My computer made a noise. You sent it to me. I'm looking in the Maths Learning Centre's revision set. No, it's all good, just as long as I know where it's coming from. Okay. And one of them is the questions and the other one's the solutions?
Yeah.
So a complex matrix has characteristic polynomial lambda cubed so I'm just checking something. So why should... Okay. So this says lambda cubed plus lambda squared plus lambda plus 1 is the characteristic polynomial. And that's lambda plus 1 times lambda squared plus 1. I'm paying attention, I think. I might just do that in smaller steps. I just want to think about this. There's a lambda plus 1 there, and if I pulled a lambda squared out of this bit, it would have a lambda plus 1 as well. Cool. My PhD in finite geometry pays off. And so my characteristic, my eigenvalues are -1 and I and minus I. Okay? And so it has as many eigenvalues as it should have, and they're all different, and there's only one of each. And so since there's only one of each, they must have the correct sized eigenspaces, and so the Jordan canonical form should just be the ordinary diagonal matrix. Okay. So the Jordan canonical form is just the diagonal matrix. Does it matter what order they're in? So just to see if I understand this Jordan canonical form thing correctly, technically this is made out of 3 smaller matrices on the diagonal of a big matrix. Okay. I'm just making sure I've got this right. And so this second one, we've got characteristic polynomial lambda squared, and the nullity is 1. Okay, so lambda cubed minus 2 lambda squared is lambda squared lambda minus 2, and so the eigenvalues are 0 and 0 and 2. Okay, so the nullity is the dimension of this subspace. Yep. Which is the eigenspace for 0. Which is the eigenspace for 0. And so therefore we have one dimension less of eigenspace than we would expect. Okay. So we have, let's just summarize. Lambda equals 0 has multiplicity 2, but its eigenspace is only 1. And lambda equals 2 has multiplicity 1, and therefore the dimension of its eigenspace must be 1. That's always true. Okay. So I won't be able to diagonalize this in the traditional way. And so my Jordan canonical form will not just be an ordinary diagonal matrix. But I suspect, that the one that does work will just be a single number in that position. Like it'll just have a 1. Like the matrix that goes with this will be a 1 by 1 matrix. No? No idea. Let's look at the solutions. There are two possibilities for the Jordan canonical form of B, namely 0, 0.
Oh, yeah.
Okay, so I've got a 2 by 2 matrix that goes with the one that appears twice, and a 1 by 1 matrix that goes with the one that appears once. And I could have a 2 by 2 matrix that goes and a 1 by 1, so that's fine. And this is the one that goes with it being an eigen, but having enough dimension for its eigenspace. And this is the one that doesn't.
So what happens here, for the first one, you have 2 Jordan blocks of zeros, right? The 2 zeros are their own blocks, 1 by 1 blocks. In the second one, you're only allowed to have 1 block because the dimension of the, like you're going to get the 1 dimensional eigenspace. And so you have a 1 dimensional block that has to be 2 by 2. And so you get the 1 on the block that just kind of appears there.
So, just to be sure of this block is going to have to be 2 by 2 because we have one less thing.
Yeah, the alternative is to have 2 1 by 1 blocks, which is what happens, like if the dimension is 2, you can have the 2 1 by 1 blocks, but that's not the case here. And because it's a bigger block, you get 1 on the left.
Okay, so it could have been this according to the notes.
That's the other alternative that is
not the one that we've got.
By the nullity condition.
And that would be.
If you're not told the nullity, then that is an option.
Okay. Right.
There is a really simple rule about how it relates to the. I think the power. What is the minimum characteristic of the answer?
Basis dimension of the largest.
Yeah, the power of the characteristic polynomial is the largest block that it can appear in, the largest size of the block.
Sorry, could you say that?
So if it's like lambda minus 1 to the n, then 1 can only be in an n by n block, a Jordan canonical block. But sometimes you can have more Jordan canonical blocks that are smaller than that, and that's determined by the power in the minimal polynomial.
There's a lot of words.
Yeah. And that wasn't clearly, that sentence wasn't clearly said in the lecture, but it's all in
Still not clearly said, just to be.
I remember the tutor drilling us with it, and then I forgot it as soon as I walked out. Something to do with the squares, how big your squares were. Yeah, that was it.
Yeah.
So the highest power in your minimum polynomial is the dimension of the largest square block.
No, isn't it characteristic?
I don't know. Maybe it's
Should we go searching for more examples?
Well, because in this example, right, if you read the polynomial back up for this example, if you like,
Yeah, it's not.
paper down there.
Sorry, where are we?
But instead of paper here, yeah. So the characteristic lambda minus 2. But the minimum polynomial would just be lambda minus 2.
Mm-hmm.
That would be the lowest order polynomial that has the roots of the things. So the square here on the lambda is the dimension of the block, of the largest possible block.
Right.
So
just a second though, if the nullity had been 0,
yeah.
2, sorry, if the nullity had been 2, it would have been this, right?
Yes.
And then the minimum polynomial would have actually been lambda squared, the same as the characteristic polynomial?
Oh, no, that's because just lambda minus 2 would still have solutions for the roots. That would still be the minimum polynomial. The only reason it isn't the one on the right is we have the condition of nullity.
But this minimum polynomial has a lambda squared in it.
That's a good point. You would think that you would think you could always get rid of
So far we have decided that it is actually confusing.
Yeah. I didn't think of that because by definition of
And is it just the 0 polynomial? Is it just the 0 eigenvalues that do that, or not? Like
Anyone that has like any multiplicity.
yeah, what is the minimum ever have anything to a power?
Google's not your friend because they write it differently. They put the ones above.
whatever.
So for some reason,
That's because they use row vectors probably instead of column vectors.
yeah, it's like transport.
Sorry?
Like normal people.
I don't know. I've been brought up to use column vectors for vectors. But
But the which of diagonal you use also doesn't matter because it still would be an invariant subspace. That's the other
And
really
it's
cool
an
one.
example of doesn't be
Yeah. Oh yeah, I just do that.
So this is from a different university. So the dimension of the lambda 1's eigenspace is apparently 2. So this says the dimension of the eigenspace being 2 tells us the Jordan canonical form of our matrix has 2 blocks that have eigenvalue 1.
Yeah, that's right. And that was the same as the nullity. That's the same piece of information that we got.
Oh, but this is a triple one, right? Okay, so you have 1 block for each dimension of eigenspace.
Yes.
So this one, this is the characteristic polynomial here, and it has 4 eigenvalues of 0 and 1 eigenvalue of 1. Oh, wow, this is a whole different thing. The dimension of the null space of A and the dimension of the null space of A squared and the dimension of the null space of A cubed. Is this a thing that you did? No? Okay. Right, this is more complicated than what we've got.
Yeah, a little bit.
So it looks like if I'm seeing this correctly, there's damn it.
There's 1 block, 1 0 block, and then 1 0 block with dimension 3.
Yeah, so we had x to the 4x minus 1. Yeah, no, I'm just writing it down so then I'll go onto the screen. And then, okay, so we want to go. So we had x to the 4x minus 1, and that meant that the lambda was 0, 0, 0, 0, and 1. And the eigenspace the dimension of the eigenspace for 0 came out to 3. Yep. Nope. No, it didn't.
No, it was 2.
Okay. And we know that the dimension of the eigenspace for 1 came out to 1. And so the matrix had a block here for this one. And then down here we have to have zeros down the diagonal like that. I understand that bit. And then they're saying that because the dimension of the eigenspace was, and theirs came out like this, and I don't understand why.
So he would tell us the ones on the other side.
Yeah, we would have ours down here.
So, yeah, I think, so the 2 blocks is the piece I understand, and you also have like the 4 eigenvalues show up there. That's not quite it. I know I've written down somewhere, it's not quite right.
I don't know. I'm sorry.
Yeah.
So the options would have been that we could have got this big 4x4 with the 1s. We could have got a single and a 3. We could have got 2 2s. Or 4 1s, yes. But we knew it wasn't that one because the dimension wasn't, the eigenspace wasn't big enough.
But how would you decide between the 2 and 2 and the 3 and 1?
Yeah. And there doesn't seem to be enough information in the course to tell you that.
It was somewhere, but not really. It made sense in the tutorial.
Made sense at the time, and then when we tried to do it, so I'm sorry, I can't figure out what information it is that tells you that. Like some of the other stuff I can make sense of. Okay, because I go, well, from the small amount of information I have, I know that it can't just be a diagonal matrix if the dimension of the eigenspaces don't work. And so that's out. And then with a 3x3, there's only one other option, and so that must be the option. And so I can certainly do that. And then there's something to do with this minimum polynomial thing. Yeah. And I don't quite understand why. This one says that their sizes of their blocks came from finding the dimension of the null space for A and A squared and A cubed, which is probably to do with the minimum polynomial.
Yeah.
Wait, what did the nullity help with in that question before?
Well, the nullity before told us that the dimension of the eigenspace wasn't as big as it should be. That's what it told me. And so it couldn't possibly be the straight-up diagonal matrix. So it couldn't be this one, because a straight-up diagonal matrix means that my original matrix was diagonalizable, and I know it wasn't because the dimension of the eigenspace didn't match the multiplicity of the eigenvalue. That's me using Maths 1b thinking.
Wait,
So it's this one.
The dimension of the eigenspace, is that the same as the nullity?
It is when the eigenvalue is 0.
Okay, so just in that case.
Yeah, so the eigenvalue, but that's what I did this. The nullity is the dimension of this, and this coincidentally is the eigenspace for 0.
Yeah. Okay.
And in all the examples so far, it's been the eigenvalue of 0 that they have been trying to figure out. Sorry?
That might be it.
So, yeah, and I wouldn't know what to do if it was something else. And my problem with this here is I don't understand how this one was produced. The 8 makes sense to me because this one only appears once anyway. The x plus 4 to the 3, I would have expected this to have maybe 1s down this diagonal, down this off diagonal.
Maybe that's the thing to do with the 0
Yeah.
thing.
So those are 4 individual blocks. Like he's hinted at with the 2, I think. The negative 4s must be 4 individual blocks.
So is it only when you have an x squared, so it's 0 turns the
that seems too...
You get ones down the diagonal for any eigenvalue. It's just this relationship about block size, about whether you have blocks of size 1 or bigger. So in that one, he's differentiating. He's explained it in 3 levels. Like you get.
Yeah, you got your big Jordan bloggers bits for the one for each eigenvalue, and then each of those is made of a Jordan matrix, which is one of these things. And this is for the number of times it appears. These are for the powers. There's one of these blocks for each of the powers. No?
This is kind of the thing, because
that's not actually true.
That's not true if your Jordan matrices are bigger than 1 by 1. Yeah. I think his index has changed at some point while he was explaining this.
So we don't know, but we have enough information to do some questions.
Yes.
Okay.
Some questions with very generous constraints.
So there is a non-zero probability of getting marks for a question about this. Because we can do some questions like this.
Yeah.
Okay. So in the intervening time between now and your exam, it would be extremely useful to go to your lecturer and ask extremely precise and specific questions about this. So and the good question is, what information helps me decide what the actual Jordan blocks are? Now, your lecturer may not be able to answer it, but this is my best chance. One of the best questions you can ask a lecturer is, how do you decide? And then if they don't give you what you need, then you can just ask again in a different way. Well, or pick something that they said and ask them about that. You say, aha, and ask them good what-if questions. So like I said, oh, so just a second, is it just the 0 ones that we have to, the 0 eigenvalues we consider? Because all the examples we have so far concern the 0 eigenvalues. All right, and say, is it something to do with how far apart these numbers are? So anytime you see them say something, like you see an example and you see a feature in the example, you can ask, this feature, is that part of the decision? That's my advice for getting lecturers to tell you what you need to know. And along the way, if you ask those questions, they are likely to tell you things like, I won't ask you situations that are like that, which tells you about your exam, but makes you feel unsatisfied about actually understanding the concept, which is sad. Yeah, so there you go. We have turned into advice about getting information out of lecturers.
I think the other thing about asking me questions, because he's really like, when I've asked him specific questions, he's explained things really well. But if I don't write them down straight away, I forget it.
Yeah, so write down the information you have, and tell all the other students.
Yeah.
Hey. Because it's not like... Tell me, and I'll tell all the other students. So I'm on holidays next week. So I may get up, if I'm up earlier than the rest of my family, I may respond to emails. Okay. That's unsatisfying, but there's nothing, I can't think of anything else to do here. I don't really understand what the decision-making process is. I know I can recognise a Jordan canonical form when I see one, but I couldn't tell you how to tell which one you have. At the very least, if I was in an exam, I would write down all the possible Jordan canonical forms I could think of that matched the information and said it's one of these. I don't know how to decide which one, but it's one of these. It's definitely not this one because, you know, that would be a diagonal matrix and it's not that, but yeah, that would be my response. Yeah. So my understanding of the Jordan canonical form is it's a replacement for the diagonal matrix. And there's supposed to be that when he says in his lecture notes that it's similar to, he means you'll be able to go some P inverse times this times A times P equals this. That's what similar means in terms of matrices. So that I do know. Because I know that similarity doesn't change the eigenvalues of a matrix. Cool. All right, so what am I going to talk about now that makes us feel like we're confident with something?
I would really appreciate it. I know this sounds kind of basic, but essentially when like Nick strings sentences together, he uses a lot of maths words in one sentence, and then you have to sit there and like unpack what each one of those words means.
Okay.
So if you could just sort of like unpack what some of the definitions or those kind of
Sure.
things were.
Have you got one in particular that you want to talk about?
Like so many. Every sentence he says, I'm like, that's a lot.
So sort of like what I was doing there, reading the notes and trying to figure out what the individual bits
Yeah.
meant. Okay.
Because a lot of the questions will like they'll have that it's a homomorphism and that it's linear and that it's this as well. And you sort of have to like break down what each of those things would mean for how to do the writing question.
Okay. Right. That's
I know that's very broad.
that's very broad, and I'm not sure how to respond to it at this time. Just let me see if I can figure out something to do.
Maybe add adjoints.
Yeah, that's what I was saying. That was on our list. It's funny because algebra is my favourite bit, but algebra 2 just seems, I don't know, dense, densely packed, which is what you're describing there. Sorry? Yeah, I mean, I actually really love groups and that sort of thing, but the vector spaces is just the whole other level. And I feel like at the end of this course there's just sort of crammed in a whole lot of random crap. Like, oh, sure, oh, we're matrices now. Okay, off we go. Okay. Okay, so the idea is that it says last time we had adjoints, so if I go a bit we might be able to find them. Does he actually define them yet? The above situation, we define the adjoint. Okay. So the adjoint belongs to a bilinear form? No? No, it doesn't. Okay, so let's just see what we've got. I'm going to just start with this definition and go backwards to find the information.
That's kind of what I mean. You have to keep looking up definitions to find the definition of the definition you're looking at.
Yep. Okay, so this says, in the above situation, damn it. So this is a direct quote.
It's definitely not a definition.
Direct quote. In the above situation, we define the adjoint L star, which sends W to V, of L with respect to the given inner products to be L star is defined to be QV inverse. Is this an of? Yeah, of LT QW. To unwind this definition, I'm going to get to that bit in a second. This is my direct quote. In order to understand this definition, I need to look at the above situation. All right. Sorry? Good start. But even without reading that, I'm going to make some guesses. One of the useful things to do in any learning situation is to try and have what you expect to be, because a change in your expectations will cause you to notice more, and so you're more likely to learn what happened there. They do it in physics all the time. So in physics, they'll do the beginning of an experiment and they'll say, what do you think will happen? And if you actually make the effort to make a prediction and then it turns out to be wrong or right, it'll be easier for you to remember it than if You just read it. So it does, doesn't it? It looks like the diagonalization thing. So in the above situation, we define the adjoint L star, which sends W to V of L. Okay, so the adjoint is a piece of information about L. That's something that I have now. Adjoint is made from L, right? It belongs to L. The adjoint L star belongs to L. This is my moral so far. That's the first thing I have noticed. And the reason I say that is that a lot of stuff in mathematics is that some things belong to other things. Eigenvalues belong to matrices. Linear, a range belongs to a linear transformation. And so they don't exist independently of the other things. Whereas a unit vector, for example, is a thing that exists all by itself. It doesn't need anything to exist other than a concept of length. Okay. All right. And we need some inner products too, and it needs inner products. Okay, cool. That's the first thing I've discovered. First two things. Let's go back and have a look at this above situation. What is the above situation? Okay. So an inner product on a finite dimensional vector space defines an isomorphism, V to V star, where V star is the dual, which is the set of all the linear transformations.
The dual is the set of homomorphisms from V into the field.
All right, the linear transformations from V into the field. I'm going to say linear transformations, that's what they are. Okay. If the inner product is that QV be this isomorphism. Sweet. Okay. And W is its own finite dimension. Okay.
Do you see what I mean now?
Yeah. Okay. Okay. So in the above situation, wow, complicated. That's what I'm thinking. Okay, so the above situation mentions inner product spaces, which we needed. That's fine. A bilinear form. A linear function from V to V star okay. Okay. And we've got an isomorphism too. Okay, so these are all the things. So we need to know what they are. But I'm going to not go all the way to the bottom. I'm going to keep going up every time I get to something that I understand and go back and figure out what it is before I get to the bottom. Okay, so, and just so that I've got an understanding of what this Q is, because that's from here. Q, we have an isomorphism which is that QV is V into V star via the inner product. Okay. Which is saying that okay, I think I might have something. Okay. So let's just go back and have a look at the inner products, because I have a feeling I've got this thing here. He said this QV of V1 of V2 is V1, the inner product of V1, V2 in V. Okay. So just working backwards in the notes, the first piece of notation going backwards from this definition is this. And I ignore this diagram, is this. And that might help me to figure out what's going on here. So even without knowing what this V star is, let's just pull this apart. So this, let's just write that bigger. Okay, so QV is a function. It takes things in V and produces things in V star. So this thing here is the result of doing QV on V1. Okay? I mean, that's what this notation means. Cool. And then the thing that I did to Q... So the result of doing QV on V1 is a thing that I can apply to V2 and therefore must be a function. So this thing here, I then did it to V2 and got an answer. And I didn't just multiply it by V2, because this is not multiplication. So it must be that V star is made of functions. So I can actually, even without knowing what V star is, just reading this notation, I can know that V star must be made of functions. Okay? This is a good start. So this, it's a function. Because I applied it to V2. Okay. And the answer to this function is a number. It's the inner product of V1 and V2 in V. Okay. So I'm thinking now that V star is made of functions that start in V and end up in numbers. Or possibly not numbers, but whatever the field is made of. Are we working in real numbers here? Do we care? Who knows? Okay, so that's what V star seems to be made of, even before going and looking at the definition. All right. Cool. And so just to be sure on this, every V1 creates a function which is made of doing V1 dot everything else. So just let me see if I can think of an example. So if I was doing, if my V was like R2, for example, then my QV of like, 1, 1, well, let's do it in R3 because that's the vector I've chosen, of 1, 1, 3 of a vector V would be 1, 1, 3 dot V, because that's what the dot, that's what the inner product of the dot product, like that. Cool. So the function that 113 is 113 dot V. Okay, I can follow that. All right. So this would be like, if I did x, y, z, it'd be like x plus y plus 3z, something like that. Okay. What do I know about those sorts of functions? I know that when they come out to 0, it would define a subspace. I don't know if that's useful, but it will. definitely. And if I did inner product on things, specific thing, inner product something, and I did like less than or equal to answer, then I would make half planes and I could do all the stuff that I did in Maths 1A with convex sets. Okay, so these are the things I know about it. I don't know if they're useful, but I'm just trying to relate it to stuff. I've seen thing.that, and it was a way of creating a convex set, because I remember doing a worked example on that once upon a time. Okay, cool. Okay. Right. So that's where we are there. That's what that bit means. And so we're going to go back to where we were up to and in our list of things. I think I understand what this bit means. Okay, and I mean, really, it's just, I'm okay with that. I mean, it says it's an isomorphism, and so that's just, I suppose, saying that the way that vectors behave in V is the same as the way that the functions that they are behave in the set of functions. Okay, cool. Right. So whether I'm dotting them with something, like whether I'm inner producting them with something, or whether I'm just thinking them as vectors on their own, they behave the same way. Well, that works. I mean, that's essentially just telling me the rules of how inner products work when you expand them out. I think. Not sure, but pretty sure. Okay, so we've got the linear function. Yes, we've got that. Inner product, I'm pretty sure I know what an inner product is. It's a thing that behaves the way the dot product behaves. But I'm just going to just checking. So inner product, you put stuff in these positions, and I suppose if you have like V, it does this thing, like AV of and W is A times V. This is right, isn't it? These are the rules of inner products. And U plus V W is U W V W, and it doesn't matter which way around it goes. And so the rules work on the other side as well. Okay. And I suppose the length, the dot product of anything with anything with 0 is 0. I think that's the last rule, probably.
Positive definite, which is that, yeah, they're greater than or equal to 0 with equality if 1 is 0.
And I think positive definite is that, so when you do it with itself, it's greater.
Yeah, with itself, sorry.
And it's only 0 if you do 0.
Yeah, because, and that's the constant formula, yeah.
Okay. Okay, cool. So that's what an inner product is, and the dot product does that, and so I'm happy with how that works. And what does it have to do with a bilinear form?
So that, sorry.
So a bilinear form is a way of making a dot product?
An inner product is a symmetric bilinear form. So some of those properties are the properties of a symmetric bilinear form that it kind of grabs onto and then has to do its own.
But I can make a bilinear form from a matrix, right?
Yeah.
Or vice versa, I can make a matrix from a bilinear form? Okay. So I'm just checking what... So a bilinear form is just a function that basically does these things?
It's a function that takes two things and is linear in both of those things.
And it produces a number?
Yeah, it goes from like V cross V into the field.
A bilinear form is the same thing as a linear function. Okay. So I just want to go back a bit and see if I can figure that. What?
Always maps to the field.
Yeah.
Oh yeah, I think there's like some added pages in there for some reason.
Skew symmetric bilinear forms. Okay, so an inner product is a bilinear form. Well, a particular kind of bilinear form. So a bilinear form is like a function equals something in the field. So I'm going to do this because it's not really a number. Okay. And bilinear is this part here. Okay. Is the expand over plus and pull out constants. Okay. And so a symmetric bilinear form has this bit as well. And a skew symmetric bilinear form would be minus if you switched it the other way. Okay? Yes. Okay. Whereas skew f of VW is minus f of WV. Okay, cool. All right, and so an inner product has to be a symmetric bilinear form. Okay. And I'm pretty sure I can make it from a matrix. So just as an example, I can go... Oh, so he called it Q, right, didn't he? All right. So e.g. if I had something like Q of V and W was like V transpose A, W, that would be a bilinear form. For a symmetric matrix. I mean, it would just be an ordinary bilinear form now, but if it was a symmetric bilinear form, it would have to be a symmetric matrix.
Yeah, that makes sense.
Okay, I'm feeling good. Okay, so this is... I feel like I'm moving away from what this definition is telling me now, so I've done a lot of stuff, and I'm feeling okay with it. This may be a helpful way of thinking about what the hell is going on here.
Writing the bilinear form like that's really good because you get the V transpose A,
Yeah.
and that is that goes from V into the homomorphism.
Okay,
That's
so,
individual, right?
so now let's go back up to our definition. Okay, so the adjoint of L, so let's just see, where are we up to? Our situation is that we have a linear transformation that goes from V into W. Yeah? No, W to crap, just a second. From V into W. And this one had an inner product. There was an inner product in V, and there was an inner product in W. And this one had a bilinear form to go with it. This one had a function to go with it, which sent V into V star. And this one had a function to go with it, which sent W into W star. That's what we had. Okay. And then we created this new thing. I need a picture. It's not a very good picture. That's basically it. Okay. When you do a linear transformation when you do a dot product, like an inner product on the result from a linear transformation, is it necessarily the linear transformation of the old dot product? No, not without using the, maybe that's what the adjoint's for. Transferring the inner products from one vector space to the other via the linear transformation. I don't know yet. I'm just guessing. Okay, and so L star sends W back to V. Like that? That much I am sure of. Okay. And then we go that L star is QV inverse L. What does this mean?
LT is a mapping from the dual of W into the dual of V. And it is kind of represented...
Okay, stop, just a sec.
Okay, yeah.
Damn it, I forgot this.
And if you go back through the notes, he writes it with a different notation. I think he writes it as L star the first time it appears, just to confuse things even more.
Yeah.
Apologize for that.
So LT.
So confused.
Okay, I was good up to here. I had V and W. They each had their own inner products, and the inner product turned any vector into a function. So the inner product turns any vector into a function, and I just stick the first vector in that position, and I do that vector with all the other vectors, and that makes a function. Okay, so I've got that bit. I've got them. Okay, cool. And then L star sends W back to V, which is fine. And then this LT is a thing that is interesting, and we're going to need to know what that is. But I'm just going to guess what this is just for a moment. Just a second. L star of a vector in W is QV inverse of LT of QW of W. That's what this says, because they're all ofs. And so this thing is a function from W to W star. Okay, so the QW is a function from W to W star. So this thing here is in W star. Okay? Sweet. Okay. And then this thing, I don't know what that is yet, but it starts in W star, definitely. So LT must start in W star and end somewhere. Doing really well. And this thing, now QV starts in V and ends in V star, so QV inverse starts in V star and ends in V. Okay, it's in V. And so this thing, this green thing, has to be in V star. So it must be true that LT takes things in W star and produces things in V star. And my guess as to the way it does that is that W star is the functions from W into the field, and V is the functions from W into the... I have no idea how this works.
We don't really ever touch the matrix LT, it just exists, but...
Presumably it's the transpose of the matrix L if we wrote this as a matrix?
Yeah, I think if it's an orthonormal matrix, the transpose works. I wrote it out, and it was really weird, and you have to write the homomorphisms as, like, the vectors in the vector space are functions, and it's really weird, but it actually kind of worked.
So now he's going to unwind the definition. He's done QV on both sides, and now he's got this. Given W in W. Oh, that's what I did. That's nice. LT of QW is in V star. That's good. If V is in V, then QV... oh yeah, right, QV of a thing is a function. And so if I enact that function on the vector V, I get this. This is saying that the inner product of W and LV in W is the same as the inner product of L star W and V back in V. So it is a way of transferring inner products from one vector space to the other. So just a second. I want to draw my picture. Here's V, here's W, here is little v, and here is little w. And little v ends up over here. This is L of little v. Yep. And the dot product of these two things is a number. Okay. And then they're saying that if I do L star of W, that'll end up back over here. And the dot product of these is also a number, so this is an inner product. And the inner product comes to the same number after all. So I feel like my diagram would be better if these went down. So I do a dot product here in W, and I do a dot product here in V, and I get the same answer. Why do I care about this? So if L is just, I mean, this seems to work no matter what L is, whether it's no matter what the linear transformation is. And L doesn't have an inverse necessarily, because if I went from like R3 to R2, I wouldn't necessarily be able to come back again, because R3 to R2 would necessarily have something in its kernel, and therefore it wouldn't be one-to-one. But apparently the dot, let's try it.
What this relationship does is let you find a matrix representing the adjoint of L, which then allows you to go back.
But it doesn't.
It does. It just isn't nice. The example.
Okay, so just a second though. Just let me think about this. If this is a smaller dimension than this is, then I can go back, but I won't. So if I did L star on L, would it come back to possibly one of the W's that went to L, went to L? If I did L star on L of V, would it produce one of the, like, would it produce V sometimes?
Sometimes.
Well, what I'm thinking is, I just want to try something. So L star of L of V would have the property that L star of L of V, just a second, L star of L of V is a thing over here in V. And it would have the property that the inner product of L star of L and V in V would be equal to the inner product of the inner product of L star of L of V and V itself back in big V, according to that rule that I forgot to write down on the paper, which says that the inner product of W and L of V in W is the inner product of V and L star of W. Oh, I like L star of W and V in V. I've written them backwards, I'm sorry. Sorry, I didn't match them up to the picture. Okay. So L star V of that. And so this should be L of V and L of V according to that rule? So according to this rule here, if you've got an L star on one side, then it's not there on the other side. And if you've got an L on this side, then it is, and you've got a non-L here, there's an L here. So you switch where the L is and it becomes a star, right? And it's changed. So L star, L of V, and V, I'll switch this L star over to the V and it'll become an L. That's how the rule works. But L of V and L of V in W is the length of L of V. Right. Okay. So, I don't know if this does anything. I don't know what this means.
Well, if L star of L of V is V, then that's just saying that they have the same length.
That the linear transformation L preserves length.
It's an isometry.
Yeah.
Which is true. I have a feeling we didn't talk about this thing because I remember getting.
I'm just trying to understand it.
Yeah.
If it really is supposed to be some sort of inverse because it goes back again, I was hoping that sometimes it produced the same thing that we started with. If we did L and then we did L star, it should come back where we came from.
There is a tutorial question on this.
Okay.
Was it the last tutorial? It was the one everyone did badly. I think it was the last one.
Wait, the assignment or the tutor?
Oh, the assignment, sorry, yeah. Because the inner product we were given was an integral, and we were dealing with polynomials, and it was really, really gross.
Yes, inner products of polynomials are usually integrals.
Yeah.
Inner products of functions are usually integrals. Okay. All right, well, I unpacked the definition. I have a feeling about what the definition means. I would really love to try it on a really specific example. And so if I just wanted to think about this, I'm going to do the most basic example I can think of and go L sends R3 to R2 by L of X, Y, Z is maybe X and Y, and we just wipe out the last coordinate. Then this says, so Q, and this is V and this is W, right? So the Q in V of, like just a vector of A, B, C is the function AX plus BY plus CZ. Okay, because it's the dot product is ABC dot, like, this function of X, Y, Z is that function, AX plus BY plus CZ. And QW of AB of XY is AX plus BY. Okay. Right. And so L star should be so L star of something here in R2 should be QV inverse LT QW of XY. Oh, this is going to be bad. Sorry?
Where do you get the LT from? Like, I don't know, from what you've done.
How do I figure out what the LT is? It may tell... Curse you, Nick Bookdahl. I can write this as a matrix, and I'm going to hope that LT is the transpose of this matrix. Like that. Z. Like that. Okay, let's hope that LT is the transpose of that matrix. Okay, so this... Only it won't be because we're working on functions. I don't know what this means. Yeah. All right, I have no idea. I know what these two things do. I know what QV inverse would do. If I had a function that looked like this, it would be the vector ABC. And so my feeling about what LT is it's the function that acts on, it goes from W star back to V star.
Here is write it as the inner product. So the inner product of L star W V in V equals the inner product of W and L of V in W.
There's too many words to
Sorry.
It's not going right. Do you want me to just...
But there's not a definition of what LT is, though, is there? Anywhere.
No.
That would make it too easy.
Do you want me to like write out what's actually what the there was kind of an example given in lecture. So like well he didn't do a whole one the whole way through. But
Well, LT must do something to the function, right?
well you can just get
That one might work.
you can get away from LT entirely because you write it out as like you do that relationship L star of
Oh, right, okay,
W.
yep, gotcha.
Yep, and then you rewrite the inner product because it's the dot product. It rewrites nicely as matrix multiplication.
So just a second, we're saying that L star of xy,
How did you get that from the lectures?
This was in the lecture.
so L star of xy and something,
Yeah, something that's in R3. Yeah.
and like, I'm going to just do DEF because I don't want to confuse myself, and this is an R3, yeah, is supposed to be the same as xy times L of DEF, yeah, in R2.
Since we know this is the dot product, this rewrites
Okay, cool. So L star of xy dot DEF is xy dot DE because that's what L of DEF is. Okay, and so this is supposed to come out to dx plus EY.
So because it's a dot product, Mick rewrite in his example he rewrites it as matrix multiplication. And then you can do something with the DEF. And then you get an expression that is the adjoint of xy.
There's a lot going on here.
Totally. Yeah, and so you can do this as a row. I can rewrite this as a row and that as a column.
Yeah.
And so I can do and so I'm thinking that this L star would have to be xy 0. Like, and this would have to work no matter what DEF was. So in particular, 100 times this should produce the first coordinate of L star xy. So 100 of L star xy is 1x plus 0. And so, therefore, and this is the first coordinate of L star xy, which is 1. Like, not coordinate, but the first coefficient of L star xy. So the first coordinate of that is x, and the second coordinate of L star xy is y, and the third coordinate of L star xy is 0, and so therefore L star xy is x, y, 0. Okay, which is what I thought was going to happen. So this function starts in R3 and produces something in R2. And what we do is we take something with coordinates x, y, 0, and we x, y, z, and we produce something over here with coordinates x, y, and that's what L does. And L star comes back and produces x, y, 0, which may or may not be the thing I started with. But is one of the things I could have started with. And so I have a feeling that that L of L star of V of W is definitely going to be W. That's my feeling. And that's what I think is going to be true. And if it were equal to W, then if I minused it from W, and did the dot product of it with itself, if I did this, so L of L star of W minus W should be 0, right? So if I did the dot product in W of the in W of this with itself, then yes, yes, okay. So when I do the dot product of this with itself, I know this is what it is over in W, yep. Then when I switch from W over to V when I do these dot products, then I can, damn it, that's not going to help. If there was an L star, then I can put one in, but there isn't. So if I switch back to V, I just want to show that this is 0. Which doesn't help. Damn it. I was really trying to show that this worked. Has my recording finished? It's almost.
Yeah, wait for it.
Sorry?
It's 3:30.
Yeah.
Yeah, that's all right. My hope is that you could get to here. So this is my feeling, and we should, if this came out to 0, it would prove that this was 0, and therefore would prove that LL star W was W. This would not make the slightest bit of sense, I think, if LL star was not the identity in W. Yeah. That's my hope. Huh. But what if, oh damn it. What if the W you picked wasn't in the range of L?
Not in the range of L, in the range of L star.
This is really weird, and
I think if you pick a W that isn't in the range or in, I don't think that makes sense in the terms of relationship.
so do we have to pick a linear transformation that's onto?
I think that's the assumption here.
Okay. All right. Sweet. So this is weird and we don't have enough experience with it to know what's going on. Well, thank you for bearing with me. At least you saw how I try and attack something that I don't already know, which may or may not help you to have strategies.